Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is flow control methods for fluid power systems. Our objective today is to recognize meter in, meter out, and bypass flow control methods used to control both the extension and retraction speed of a cylinder. Additionally, we'll recognize advantages, disadvantages, and appropriate circumstances for the application of each flow control method. Let's start this discussion with a brief review about extension and retraction of a hydraulic cylinder. A double-acting cylinder has both a cap end port and a rod end port. When pressurized flow enters the cap end, obviously the cylinder extends. What may be obvious, but only secondarily important at this point in your fluid power career, is that while the cylinder is extending, fluid is leaving the rod end at a certain flow rate. My question to you is this: what determines extension speed? The flow rate entering and filling up the cap end volume, or the flow rate leaving and draining the rod end volume? The answer is both. If one wanted to limit the extension speed, one could limit the input supplied to the cap end, or limit the amount exhausted by the rod end. Both methods would effectively control the extension speed of our actuator. Limiting the input flow rate supplied to our cap end is obviously going to control the speed at which the cap end volume fills. If it is allowed to fill quickly, the cylinder will extend quickly. If the flow rate is throttled down, this same space will fill slower and the cylinder will extend slower. Controlling or metering the input flow rate is easy to understand how it controls extension speed. Hence the name meter in extension. The output side takes a little bit of visualization to understand. If you've been actively involved in a hardware lab supporting these lectures, you've probably run across an occasion where a double-acting cylinder with a blocked rod end port would not extend. The reason is that the fluid trapped inside the rod end volume has no place to go and is incompressible. Therefore, the cylinder, for all intents and purposes, has reached the limits of its travel early, and pressure rises until the pressure relief valve is actuated. This, if you think about it, is also a means of flow control on the output. Granted, with a completely blocked rod end port, you're not allowing any flow. But imagine if this completely blocked rod end port was in fact a shut-off valve, and you cracked it just the tiniest little bit to let the rod end fluid trickle out at a slow rate. The cylinder would initiate a slow extension. Now, replace the shutoff valve being used for a purpose it wasn't intended for with a flow control valve and let it do what it is intended to do, namely control flow. By throttling this valve up or down, we control or meter extension speed by controlling not the input flow rate, but the output flow rate, hence the name meter out extension. These meter in and meter out configurations are not limited to extension only. There are occasions we wish to control retraction speed. Let's again start with a review of basic retraction for a double-acting cylinder. When pressurized flow enters the rod end, obviously the cylinder retracts. While the cylinder is retracting, flow is leaving the cap end. Again, my question to you is this: what determines retraction speed? The flow rate entering and filling the rod end volume, or the flow rate leaving and draining the cap end volume? The answer again is both. If one wanted to limit the retraction speed, one could limit the input supplied to the rod end in a meter in retraction configuration, or limit the amount exhausted by the cap end in a meter out retraction configuration. Both methods would effectively control the retraction speed of our actuator. If we limit the flow supplied to the rod end, this is meter in retraction. If we limit the flow exhausted by the cap end, this is meter out retraction. Take a moment to sit back and contemplate the four diagrams I've drawn. You'll notice that superficially, these flow control methods look kind of the same. There are flow control valves on either a rod end or a cap end. Your instructor has randomly assigned them funny names, and now he wants you to memorize them. No. Memorization is for people that don't have the internet. I want you to think about it. I want you to feel it. I want you to understand it. What are these flow control valves with check valve bypasses doing? Why are they doing it? And importantly, how does the orientation of the check valve bypass influence which flow control method, meter in or meter out, and which action, extension or retraction, it controls? Obviously, the check valve bypass is a means of bypassing the flow control valve. When it's run in one direction, it's controlling or metering flow. When it's run in the opposite direction, it's bypassing the flow control valve and allowing free, unrestricted flow. This is important for two reasons. When run in the controlled or metered direction, it's limiting either the extension or retraction speed, depending on where it's located. However, when run in reverse, let's say because someone has switched the position of a directional control valve, it's performing the opposite action at full speed. Given one could have flow control valves on either the rod or cap end control extension or retraction, the orientation of the check valve bypass is the single most important clue as to which flow control method is being utilized. Remember this fact. Take, for example, meter in extension. When run in this direction, it is controlling extension speed. However, when reversed, does not retard retraction at all because of the check valve bypass. Consider the function of the check valve bypass for meter out extension. When run in this direction, it is controlling extension speed by limiting flow rate leaving the rod end. However, when reversed, does not retard retraction speed at all because of the check valve bypass. Consider the function of the check valve bypass in meter in retraction. When run in this direction, it is controlling retraction speed. However, when reversed, does not retard extension at all because of the check valve bypass. Finally, consider the function of the check valve bypass in meter out retraction. When run in this direction, it is controlling retraction speed. However, when reversed, does not retard extension speed at all because of the check valve bypass. Notice every single one of these occasions, it is the orientation of the check valve bypass that is ultimately determined in the method being utilized. The flow control valve will only control flow when it is allowed to do so. You might have the most accurate flow control valve in the world, but if it's being bypassed, it isn't controlling anything. Only when the check valve bypass selectively blocks flow can the flow control valve be used to meter in extend, meter out extend, meter in retract, or meter out retract. By all means, take the time necessary to copy these different flow control configurations into your notes. Hint, hint. Be aware no single flow control method can be used for all possible circumstances, and one must properly consider costs and benefits and advantages and disadvantages of each method. For example, which action you wish to control, extension or retraction. Is it cost effective for an industrial process to simply control one action and not the other? For example, consider an application in which only extension speed needs to be controlled, and retraction can happen as fast as the pump can provide flow. Is it truly cost effective to have multiple sets of hardware controlling both extension and retraction speed when one would suffice? I don't know. The necessities of the process determine this. If you need to accurately control both actions, you're stuck with buying, installing, and maintaining more equipment. Let's say your industrial process requires equal extension and retraction speeds. Given retraction already occurs faster than extension for a constant flow rate because of the volume differential between the cap end and the rod end volumes, one could simply size the cylinder dimensions and pump flow rate for the necessary extension speed and then limit retraction speed in your choice of meter in retraction or meter out retraction arrangements. Like I said, the possibilities are limitless. In a strictly horizontal sense, when actuators push or pull a force that is not acted on in any other direction other than horizontal, one can expect your chosen flow control method, whatever it is, to control that action, extension or retraction appropriately. However, in the case of a controlled descent of a suspended object or the movement of an overrunning load, the selection of the proper flow control method is vitally important to your safety and proper functionality of the circuit. In both these circumstances, the outside environment, i.e. gravity, is providing force in addition to the input and output pressure. If a lifted object is supported by fluid under pressure, and suddenly that pressure is gone, it does not matter how well you're controlling the input rate. The object will crash to the ground. Same thing for an overrunning or tilted load. Once it reaches the tilt point, if there isn't another set of hands on the other side slowing it down, it will crash to the limits of travel, and maybe beyond if there's nothing to support it on the other side. Even if the suspended object survives an uncontrolled descent, consider the damage incurred to the fluid power components for such a situation. Not only is the piston face slamming against whatever limits its travel, think about the fluid on the other side of the piston face. As the piston face rips away from this fluid, it creates a rapid depressurization where the fluid leaves its liquid phase and enters the vapor phase, only to be compressed and implode when pressurized flow on the input side finally catches up. This is a cavitation event and will seriously limit the lifetime of your components. These applications are most rightly suited for meter-out flow control methods. The check valve bypass allows the opposite action to happen at full speed. However, by limiting the amount of flow leaving the supporting side, it means you have a column of fluid still under pressure supporting the load. By placing the flow control valve on the output stream, we can now drain it in a controlled manner so our object descends in a controlled manner and a cavitation event does not occur. Be aware certain meter-out configurations may result in pressure intensification beyond that of the system pressure relief valve due to area imbalances between the cap and rod end. For example, a suspended load hanging from a cylinder which lifts when retracted and lowers when extended. When extending to lower the object, both the input pressure supplied to the cap end and the lifted object are exerting pressure on the smaller rod end area. It's like an elephant and an elephant seal, both standing in the same donut-shaped area. Despite the fact that your pressure relief valve may be limited to, let's say, 700 psi, when this same input force and the lifted object are acting on the smaller area, obviously pressure in the rod end leg will be higher than 700 psi. One must take pressure intensification into account when specifying components and connectors for a system. Meter in extension, meter out extension, meter in retraction, and meter out retraction are four means of directly controlling cylinder actuation speed. When a flow control valve not being bypassed is placed in any of these paths, it creates a narrow passageway through which only a portion of the flow can negotiate. A pressure differential occurs across the input and output ports of the flow control valve, causing pressure to rise in the portion upstream of the flow control valve. An excess flow is diverted through the pressure relief valve. This is to suggest that restriction-style flow control valves and direct restriction flow control methods work in combination with the pressure relief valve. Flow in always equals flow out. This is kind of like the Kirchhoff's current law of hydraulics. Incoming flow has to go somewhere. That flow not admitted through the flow control valve is relieved at the pressure of the pressure relief valve. When pressure drops without having accomplished work, there's a rise in temperature, a form of inefficiency. In addition to these direct means of controlling flow to an actuator, there exists another means called bypass or bleed off, using indirect means to do so. This method returns excess flow to the tank below that of the pressure relief valve setting. And although an indirect method of controlling flow is more efficient because the pressure relief valve is not actuated in the process. Simply by diverting a portion of unused flow to an actuator, i.e. bypassing or bleeding it off, and allowing the remainder of the flow to continue onto the actuator, we've indirectly controlled the extension or retraction speed. Again, this is kind of like the Kirchhoff's current law of hydraulics. Flow in always equals flow out. If our pump is supplying 3 gallons per minute and 1 gallon per minute is being purposely diverted or bled off, only 2 gallons per minute is available to extend or retract our actuator. If we wish to slow our actuator down further, we would open up the bypassing or bleed off flow control valve up more, not close it down as in our earlier direct restriction configurations. This way, the bypassing flow control valve bleeds off more of the incoming flow and less is available for the actuator. Realize in a bypass or bleed-off configuration, the pressure relief valve is not being actuated and the excess flow is being returned to our tank at the pressure which is required to move our load. Say for example, our load requires 400 psi of pressure to extend and the pressure relief valve is set at 700 psi. The pressure differential across the flow control valve now is only 400 psi and not the 700 psi across the main pressure relief valve. There is still a temperature rise in inefficiency, however it's less than our previously direct controlled configurations. While one can control extension and retraction speed using bypass or bleed-off flow control methods, it's probably not the best configuration for the controlled descent of a lifted object or a tilted load, because it does not allow for the controlled emptying of a fluid power actuator supporting a load. It only diverts supplied flow away from an actuator. You'd have to use a meter-out configuration or a counterbalance valve, a type of pressure control valve we'll be talking about in later lectures to do this. Here are a couple clips from experimental verification of different flow control methods. In a meter-in extension configuration, I can control the speed of extension by limiting flow input to our cap end. The first time I extend and retract the cylinder, the flow control valve is all the way open and essentially allowing everything to happen at full speed. Notice the speed of retraction is still quicker than that of extension because of the volume imbalance between the cap end volume and the rod end volume. It takes longer to extend because it takes longer to fill up the cap end volume. It takes less time to retract because it takes less time to fill up the smaller rod end volume. As I continue to decrease flow supplied to the cap end, notice the extension speed goes slower and slower. Notice retraction speed is unaffected because of the check valve bypass. Additionally, notice that the pressure gauge I've placed on the upstream side of the flow control valve rises while the cylinder is extending. This is the pressure rise due to the pressure differential created by the narrow passageway. This flow control method could be used to control the speed of an actuator used to push a supported object horizontally. Consider, however, the limitations of meter-in extension and controlling the speed of a lifted or overrunning load when gravity comes into play. When unloaded, the cylinder with meter-in extension configuration extends at a controlled speed. However, when a cylinder in this orientation is loaded, the retracting rod will lift the object, but when extended, the lifted object crashes to the ground. A flow control valve in a meter-in extension configuration does limit flow to the cap end. However, the rod end is at tank pressure when extending and has no pressure to support the lifted object. Not exactly the best application for a meter-in extension configuration. In a meter-out extension configuration, one can also control the speed of extension by limiting the flow leaving the rod end. As I continue to decrease flow leaving the rod end, notice the extension speed goes slower and slower for subsequent iterations. Notice retraction speed is unaffected because of the check valve bypass. Additionally, notice that the pressure gauge I've placed on the upstream side of the flow control valve rises while it is extending. This pressure rise is due to the pressure differential created by the narrow passageway. In this case, pressure intensification in excess of our relief valve setting can occur because of the imbalance between our cap and rod end area. Same force, less area equals more pressure. You must take this intensification into account for components, hoses, and fittings. A meter-out extension configuration is a much better fit for a cylinder oriented such that it lifts when retracted and lowers a suspended object when extended. Notice we can smoothly and safely lower the lifted object at whatever speed we desire. Consider, however, the pressure intensification occurring at the rod end in this configuration. Not only is input pressure from the cap end acting on our smaller rod end area, the weight is also acting on this same smaller area. Here's a shot of the gauges again reading input and output pressure of the flow control valve. Despite the fact that the relief valve is set to 500 psi, we are clearly in excess of it in the rod end leg for this meter-out extension configuration, that lowers the suspended object when the rod extends. The meter out extension configuration does allow for the controlled descent of a lifted object, but you must take into account pressure intensification. In a meter in retraction configuration, I can control the speed of retraction by limiting flow input to our rod end. As I continue to decrease flow rate supplied to the rod end, notice the retraction speed goes slower and slower for subsequent iterations. Notice extension speed is unaffected because of the check valve bypass. Additionally, notice the pressure gauge I've placed on the upstream side of the flow control valve rises while it is retracting. This is the pressure rise due to the pressure differential created by the narrow passageway. Somewhere in here is a point when both extension and retraction are occurring at the same speed. Consider, however, the limitations of meter in retraction and controlling the retraction speed when outside forces come into play. Here I'm using a spring loading device to push back on the cylinder. When the cylinder retracts, the spring loading device simply slams forward despite variations in flow rate supplying the rod end. A flow control valve on the input of the rod end in a meter in retraction configuration does limit flow to the rod end. However, the cap end is at tank pressure when retracting and has no pressure to counteract the outside force. Not exactly the best application for a meter in retraction configuration. In a meter out retraction configuration, I can also control the speed of retraction by limiting flow output from our cap end. As I continue to decrease flow rate leaving the cap end, notice the retraction speed goes slower and slower for subsequent iterations. Notice the extension speed is unaffected because of the check valve bypass. Additionally, notice the pressure gauge I've placed on the upstream side of the flow control valve rises while it is retracting. This is the pressure rise due to the pressure differential created by the narrow passageway. In this case, intensification is not occurring because the cap end area is larger than that of the rod end area. Same force, larger area equals less pressure. A meter out retraction configuration is a better fit for a cylinder resisting an outside force, such as gravity or a tilting load. Notice we can smoothly and safely bring the spring loading device to a rest at whatever speed we desire using a meter out retraction configuration. In this case, the flow rate leaving the cap end is purposely dialed down, leaving a quantity of pressurized fluid in the cap end to counter the externally applied force. In a bypass extension configuration, I'm purposely diverting a portion of the flow supplied to our cap end away from the actuator. With the flow control valve completely closed and no flow being diverted, the cylinder extends as if there is no flow control valve in the system. However, when I progressively open the flow control valve more and more, less flow is available to extend our actuator and it moves slower and slower. Retraction speed in this configuration is unaffected. One could also create a bypass retraction configuration where a portion of the flow input to our rod end is being purposely diverted. That's it. In conclusion, this lecture presented meter in, meter out, and bypass flow control methods to control both the extension and retraction speed of a cylinder actuator. Additionally, we recognize certain flow control methods should not be utilized for occasions of a suspended or overrunning load and may call for alternate methods. Finally, we can anticipate pressure intensification for certain flow control configurations that may need to be accounted for in the design and safe operation of a fluid power system. The take-home point is that the orientation of the check valve bypass is the single most important determining factor for flow control methods. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.